Every skyscraper has blueprints, that detailed plan.
Mm-hmm.
And every successful tech innovation, think about the apps on your phone or maybe the big corporate networks, they have something just as vital.
Right. IT, project quality management,
Yeah.
PQM.
Exactly. Without that structure, that digital blueprint, well, even the most ambitious ideas can just collapse before they even launch.
That's the reality, isn't it? The digital world, it doesn't just succeed by luck or, happy accidents. It succeeds because of rigorous PQM. It's the discipline that makes sure we don't just build something.
Right.
But that we build the right thing.
Yeah.
And that we build it reliably, consistently, securely. That's crucial today.
Welcome back to the deep dive. Our mission today really is to cut through all that complexity and pull out the core concepts of PQM, the foundations, and maybe some advanced stuff too.
Yeah, we're diving deep. We've got a good stack of sources here, foundational project management texts, some really rigorous Six Sigma stuff, and of course the big one, ISO 9001 standards.
And this is essential stuff if you're currently, say, starting your graduate coursework.
Oh, absolutely. Especially, thinking about that group project, You're likely acting as a project manager or really active team member there.
So this isn't just theory.
Not at all. This deep dive is, frankly, non-negotiable. You're not just learning definitions here.
No.
You're picking up critical skills you'll need for professional success. It helps you understand where project management even came from.
Yeah, it's Genesis.
Right, it's Genesis. And maybe most importantly, how it demonstrably improves the success rate of IT projects. That's the bottom line.
That real-world application, yeah, that's the goal. So before we jump into the deep end, just a quick reminder. Please like, follow, share this deep dive if you find it useful. And check the description, too. We've put some resources there linking this classroom stuff directly to, future career paths.
Yeah.
Quality assurance, project leadership.
Good stuff in there. Okay, shall we kick things off?
Okay, let's unpack this core idea, PQM. Where do we even start? What exactly is project quality management? Sometimes it sounds like, bureaucratic overhead.
Yeah, it can sound like that, but it's the heart of project success, truly. PQM is essentially the whole process, all the activities that make sure a project will satisfy the needs.
The needs it was started for.
Exactly, the needs for which it was undertaken. Sounds simple, right?
Deceptively simple.
It is, because those needs can be really complex. It's about meeting or, ideally exceeding customer needs and expectations.
And that means focusing on the customer's viewpoint.
Critically important. You've got to focus on the customer's view of quality. We see it all the time, projects that technically meet every single spec.
Check all the boxes.
Check all the boxes, but they utterly fail the user. They're unusable or don't solve the real problem. That's why adopting the customer's perspective is just paramount.
That focus is so important.
Yeah.
Because what the project team thinks is quality, maybe elegant code, right?
Sure, happens a lot.
That might be totally irrelevant if the system is, painfully slowed or impossible to navigate for the actual user.
Precisely.
So our sources break this down. They give us 3 core concepts for quality that honestly get mixed up a lot out in the field. Let's try and nail those down.
Yeah, we absolutely need to be precise with the language here. It matters. So first, just quality itself. What is it?
Okay.
The definition is the degree to which a set of inherent characteristics fulfills requirements. Or, stated or implied needs.
Stated or implied. What's the difference there?
Good question.
Go ahead.
Stated needs are the ones the customer explicitly tells you. They're in the written specs, maybe verbal instructions you got.
Clear requirements.
Hopefully clear, yes. But then you have the implied needs. These are just as vital. They essentially mean the product has to be fit for its intended use.
Okay.
You build a mobile app. The stated need is the list of features, right? Calculate this, display that. The implied need is that the app doesn't, say, drain the user's entire phone battery in an hour or crash constantly. That wasn't written down, but it's absolutely a quality requirement. It has to be fit for use.
Got it. And then the next 2 definitions. This is where teams can really get into trouble, right? Conformance to requirements versus fitness for use.
Correct. This distinction is crucial. Conformance to requirements. That means the project processes and the product itself meet the written specifications, the stated needs we just talked about.
So it does exactly what the document says it should do.
Exactly. It's kind of the minimum bar. If you ask for a system that processes 100 transactions per second and you test it and it does exactly 100, it conforms.
Sounds good.
It sounds good. But here's the catch. What if the business environment changes completely during the project? Or what if the initial specification was just wrong, fundamentally flawed? Then, even with high conformance, the project can still be a massive failure.
Because it's not actually useful anymore.
Precisely. Which brings us to the ultimate measure, fitness for use.
The acid test, you called it.
It really is. The product must be usable as it was intended in its real operating environment. Let's take an example. Imagine an energy trading platform project.
Okay.
The spec says it must handle, say, 1,000 concurrent user sessions. The team builds it, tests it rigorously, confirms, handles 1,000 sessions. High conformance, right?
Checks the box.
Checks the box.
Yeah.
But the implementation required some super technical proprietary operating system that none of the client's existing IT staff know how to manage or maintain.
Oh, dear.
And maybe the user interface is incredibly complex. It needs like 3 hours of intense training just for a trader to place a simple order.
So technically it works, but practically?
Practically, it's a disaster. It conforms to the load requirement, sure, but it is absolutely not fit for use by the client's actual workforce. It's unusable, unmaintainable, that project. It's a quality failure, despite conformance.
That clarity helps so much. Okay, so PQM isn't just a single check at the end. It's a whole life cycle.
Definitely a life cycle.
And our sources map this out. They talk about 3 core PQM processes that project managers are cycling through again and again.
That's the structure. You've got planning quality management, then managing quality, which is often called quality assurance, and finally, controlling quality. Plan, manage, control.
Let's start at the beginning then. Planning quality management. This is the upfront strategic piece, right? What does the PM have to define here?
Planning is all about defining the relevant quality standards for this specific project. You might reference industry standards like ISO 9001 or internal company standards.
Okay.
And then you outline exactly how the project is going to meet those standards. How does this relate to the project scope? How will we verify it?
And you mentioned linking it to design of experiments.
Yeah, often when planning IT project quality, we draw on principles from design of experiments, or DDO. It's a powerful statistical technique.
How does it help here?
Well, DOE helps you systematically figure out which factors, which variables, have the most influence on the outcome you care about, in this case, quality.
So instead of just guessing what testing method is best.
Exactly. You could use DOE to figure out, say, which combination of testing inputs, maybe automated integration tests versus manual user acceptance testing, produces the highest software reliability for the effort invested. It helps optimize your quality approach.
Makes sense. So what specific things are we considering in this planning phase?
We usually focus on about 6 key aspects. First, obviously, is functionality. Does it perform the intended function? Basic, but essential.
Table stakes.
Pretty much. Then, features. These are the special characteristics, the things that appeal to users beyond basic function. Think single sign-on or maybe mobile compatibility, the bells and whistles sometimes. Then, performance. How well does it do its job? Latency, throughput, speed of calculations, response time, all that.
Okay. Performance. What else?
Next come durability and resilience. Reliability. Does it perform as expected under normal, defined conditions? Does it crash unexpectedly?
Crucial for user trust.
Absolutely. And closely related is maintainability. How easy is it to fix bugs? To apply patches, make updates? If it's a nightmare to maintain, quality suffers long-term.
Right. The total cost of ownership goes way up.
Exactly. And finally, we look at the system outputs. These are the tangible things the user interacts with: the screens, the reports, data visualizations. Are they clear, accurate, useful? This is often where the user perceives quality.
That's a comprehensive list.
Yeah.
So once that detailed plan is hammered out, we move into execution, which involves managing quality or quality assurance.
Correct. Managing quality, or QA, happens continuously throughout the project. It's sometimes called the management section of PQM.
Okay.
It's the periodic, ongoing evaluation of the overall project performance. Are we actually following the plan? Are we meeting the standards we set out? This is where leadership, senior management has a huge impact. By actively championing and supporting the quality assurance system, QA is about building confidence for the team, for stakeholders, for the customer, that the final product will meet the requirements. Management backing makes that possible.
So what are the specific tools or techniques used in QA to make it actionable? How do we actually do assurance?
2 crucial tools here are benchmarking and quality audits.
Benchmarking, like comparing ourselves to others.
Exactly. You generate ideas for improving quality by comparing your specific project practices or maybe product characteristics to those of other projects. Could be internal projects, could be industry best practices.
Example.
Sure, maybe your team takes 3 weeks to deploy a software patch. You benchmark against a similar team, maybe in another division or even another company that does it in just 3 days.
And you figure out how they do it.
Right. You analyze their process to understand the gaps in yours. It provides concrete targets for improvement.
Okay, and the other one, quality audits.
A quality audit is a structured, formal review of your quality management activities. Are we following the defined processes? Are they effective? It identifies lessons learned, what worked well, what didn't work so well.
So it's not about blaming people.
Absolutely not, or it shouldn't be. It's a proactive, systematic health check for your quality system. The goal is to feed information back to improve performance, either on the current project or for future ones. It's not a fault-finding exercise. It's about process improvement.
That makes sense. Planning sets the stage. Assurance checks the overall performance during execution. Which brings us to the final piece, which is also ongoing. Controlling quality. This sounds more hands-on.
It is. Controlling quality is the monitoring phase. This is where you monitor specific project results, the actual deliverables being produced, the process metrics you defined to ensure they comply with the standards set in the plan.
Measuring things.
Measuring things, comparing them to the standard, and figuring out what to do about deviations. But there's an important philosophy here. If you plan quality well up front, and you assure the processes consistently throughout, you should minimize the need for painful control actions later.
Prevention versus cure.
Exactly. Effective planning and assurance help avoid rework. Controlling quality often responds to problems that have already occurred, though it also aims to prevent future ones.
Okay, so control isn't just monitoring. It generates direct, actionable results. What are the main outputs from this process? What happens when you find something off spec?
Yeah, it translates directly into action. The main outputs are typically acceptance decisions, rework, and process adjustments.
Acceptance decisions.
Yeah.
That's pretty straightforward. Pass or fail.
Basically, yes. Is this specific deliverable, this piece of code, this document acceptable, or is it rejected based on the quality criteria?
And if it's rejected?
That leads to rework. That's the action taken to bring those rejected items back into compliance. Fixing the bug, rewriting the section, rerunning the test.
Standard stuff. What about process adjustments? That sounds different.
It's more strategic. Process adjustments are corrections or changes made to the underlying process itself to prevent similar quality issues from happening again in the future.
Fixing the root cause.
Exactly. So let's say a tester rejects a piece of code that's an acceptance decision.
Okay.
The developer fixes the specific bug, that's rework.
Right.
The project manager might then look at why that bug occurred and decide to implement a mandatory peer review step before code check-in for that type of module. That's a process adjustment. It aims to catch that specific type of error earlier next time.
Okay, that clarifies the 3 main processes.
Yeah.
Plan, manage, control. But once we understand what controlling quality involves, we need the actual tools to do it effectively.
Right. How do you measure? How do you analyze?
Exactly. Which brings us to a really practical set of techniques, often called the 7 basic tools of quality. These sound like the real workhorses for quality throws.
They absolutely are. You could call them the foundation of beta-driven problem-solving in quality management. They were standardized and really popularized by the quality pioneer Kaoru Ishikawa.
Ishikawa. I know that name.
Yeah, famous for the fishbone diagram we'll get to.
Yeah.
His goal was brilliant: to democratize statistical thinking, to make these powerful quality principles accessible to everyone in the company, not just the statisticians with PhDs.
So these tools help replace gut feeling with actual data.
Precisely. They allow teams to move away from intuition or assumptions about what's wrong and instead use quantifiable data to identify and solve problems, essential for effective quality control.
All right, let's break them down. 7 indispensable tools.
Yeah.
Where do we start? Maybe with the one for finding the source of the problem.
Good place to start. That's the cause and effect diagram. You probably know it better as the fishbone diagram or the Ishikawa diagram.
The fishbone, yeah. Looks like a fish skeleton.
It does. Its purpose is systematic root cause analysis. You start with the problem, the effect, maybe customer complaints about slow loading times. That's the head of the fish.
Okay.
Then you brainstorm potential causes and group them into major categories, which form the bones branching off the spine. The goal is to trace that effect back to its ultimate source, the root cause.
And there's a specific technique used here, isn't there? The 5 whys.
Exactly. It's a really powerful, simple technique. You state the problem, and then you just keep asking, why did this happen? Repeatedly.
Like peeling an onion.
Like peeling an onion, yes. Each why peels back a layer of symptoms until, hopefully around the 5th why, you arrive at the fundamental actionable root cause.
And the categories on the bones, are they standard?
Often, yes. In manufacturing, you see the classic 5M1E: man, people, machine, method, material, measurement, and environment.
Right.
But for IT projects, those don't always fit perfectly, so we often adapt them. A common IT structure is the 4S. Surroundings, like the work environment, company policies, suppliers, vendors, third-party APIs, hardware providers, skills, team training, experience levels, personnel issues, and systems, the actual hardware, software, network architecture.
That makes sense. Tailoring it to the IT context. Help teams categorize causes relevant to software or infrastructure problems.
Definitely.
Okay. Tool number 2, the check sheet. This sounds simpler.
It is simpler, but don't underestimate its power. Check sheets, or sometimes called tally sheets or checklists, are purely tools for organizing facts to make data collection easier and more consistent.
So just counting things.
Often, yes. They're particularly crucial for gathering attributes data. For example, tracking the frequency of different types of defects found during a software code review, or maybe noting the location where errors occur most often on a web form.
What makes it powerful then if it's just counting?
The consistency. A well-designed check sheet ensures everyone collects the same data in the same way. This prevents bias creeping into your data collection and allows you to move reliably from just raw observation to actual quantifiable analysis later on. It makes the data trustworthy.
Got it. Okay, moving into more statistical territory now. Tool number 3, the control chart, also called a Shewhart chart. This sounds fundamental for process control.
It is. Control charts are really the backbone of statistical process control, or SPC. They are vital for determining if a process is stable and predictable over time.
Stable and predictable, meaning in control.
Exactly. Is the process in control? A control chart displays your data points measurements taken over time, plotted relative to a center line, which is usually the process average or mean.
Okay.
And crucially, it includes an upper control limit, UCL, and a lower control limit, LCL. These limits are not specification limits set by a customer.
Important distinction.
Very important. Control limits are calculated statistically from the process data itself. They represent the natural inherent capability or variation of the process when it's stable.
So what's the key insight you get from a control chart?
The key insight is this. If a process is stable and in control, all the variation you see between the data points within those control limits is just random noise. It's expected common cause variation.
Okay.
But if a point falls outside the control limits, either above the UCL or below the LCL, that's a signal. It tells you something non-random, something specific has affected the process. That's called an assignable cause or special cause variation, and you need to investigate it.
So it flags unexpected problems. But I remember reading about another rule, something about points inside the limits.
Yes. This is critical and often missed, the 7-run rule. It's a key test for non-randomness even when all points are technically within the control limit.
How does that work?
If you see 7 consecutive data points that are all above the center line, or all below the center line, or all continuously increasing, or all continuously decreasing, that pattern signals a non-random problem.
Even if none of them cross the control limits?
Even if none cross the limits, it tells you that something systematic has likely shifted the process average or introduced a trend. The process might still be capable of meeting specs, but it's no longer statistically stable or predictable. It needs examination.
Can you give an IT example of the 7-run rule?
Sure. Let's say you're tracking the time it takes your help desk to resolve high-priority security bugs each day. You plot this on a control chart.
Okay.
Maybe your average resolution time is 4 hours, with control limits at 1 hour and 7 hours. For 6 days, the times are maybe 3, 5, 4, 6, 3, 5 hours, bouncing around randomly inside the limits.
That seems fine.
But then, for the next 7 days straight, the resolution times are 5.5, 6.5, 6.55, 6, 5.5 hours. All are above the 4-hour average, even though none hit the 7-hour upper limit.
Ah, the 7-run rule kicks in.
Exactly. That pattern tells management. Stop. Even though we're still meeting the formal SLA perhaps, something fundamental in our support process has shifted or degraded. We need to investigate why resolution times are consistently higher now. It prompts action before a limit is breached.
That's a really practical application. It turns abstract stats into an immediate management signal. Okay, tool 4 helps us decide what to act on, the Pareto chart.
Yes, the Pareto chart, named after Vilfredo Pareto, and it leverages the famous 80-20 principle.
The vital few and the trivial many.
That's the one. The idea is that typically a large majority of problems or effects, maybe 80%, are caused by a small minority of causes, maybe 20%. The Pareto chart helps you identify those vital few contributors.
How does it display that?
It's essentially a specialized histogram, a bar chart. It ranks your problem areas, types of defects, sources of customer complaints, reasons for delay in descending order based on their frequency or sometimes their consequence, like cost.
So the tallest bar on the left is the biggest problem.
Right. And it often includes a line graph superimposed on the bars, showing the cumulative percentage. This line makes it really easy to see which few categories account for, say, 80% of the total issues.
So back to IT projects. If a software project has, 10 different categories of bugs being reported, the Pareto chart would quickly show the development team, look, focus your fixing efforts on these top 2 categories first. Fixing just those will eliminate maybe 70 or 80% of the total bug count or user impact.
Exactly. It forces prioritization based on data. It ensures that your limited resources, time, money, people are focused on the problems that will give you the biggest bang for your buck in terms of quality improvement.
Makes total sense. Okay, tool number 5 is the histogram. Now you said the Pareto chart is a type of histogram. So what's the difference? Why is the basic histogram listed as a separate tool?
Good question. They are related but serve different purposes. A standard histogram is a graphical bar chart that shows the frequency distribution of a single variable.
Wow.
How often do different values occur in a data set?
Okay, so it gives you a picture of the data's shape.
Precisely. It helps you understand the data's central tendency, where's the peak or center, its dispersion or spread, how wide is the distribution, and its shape. Is it symmetrical like a bell curve? Is it skewed to one side? Does it have multiple peaks?
So how does that differ from Pareto or maybe even the control chart?
The critical distinction, especially versus the control chart, is that the histogram does not consider the influence of time. It gives you a static snapshot of the overall variation in your data set at one point in time, or aggregated over a period.
Whereas the control chart tracks variation over time to see if it's stable.
Exactly. And the Pareto chart specifically ranks categories of problems by frequency to aid prioritization, while a standard histogram just shows the distribution of a single continuous variable, like cycle time measurements. Different views for different questions.
Got it. Okay, tool 6 moves us into relationships between variables, the scatter diagram.
Right. The scatter diagram, sometimes called a scatter plot or a correlation chart. This tool is used to explore the potential relationship between two variables. You plot ordered pairs of data, x, y, on a graph.
Like what kind of pairs in IT?
For example, you could plot developer experience in years, that's your x variable, the independent one, against the number of bugs introduced per 1,000 lines of code. That's your y variable, the dependent one. Each dot on the chart represents one developer.
And you're looking for a pattern in the dots.
Exactly. You look for correlation. If the dots tend to form a pattern sloping downwards from left to right, that suggests a negative correlation.
Meaning, as experience X goes up, bugs Y go down.
Right. If they slope upwards, that's a positive correlation. As X increases, Y increases. If the dots are just scattered randomly with no clear pattern, that suggests zero correlation. No obvious relationship between those two variables.
And if you do see a correlation?
If a correlation appears likely, you can then use statistical techniques to calculate a regression line, a line of best fit through the data points. This line can help you estimate or predict how much a change in the X variable might influence the Y variable.
So you could potentially predict how much additional training X might lead to a reduction in future defects. Why?
Potentially, yes. It helps quantify relationships, moving beyond just saying experience seems to matter.
Useful. Okay, last one. Number 7, stratification. This one sounds a bit different. It also mentions flowcharts here.
Stratification is more of a data analysis technique than a specific chart type, although it often uses other charts. The core idea is to separate your data into distinct categories or layers known as strata based on different factors.
Like what factors?
Could be anything relevant. Data collected by different shifts, from different machines or servers, by different teams, from different customer segments, using different suppliers, in different geographical locations.
Yeah.
Get the idea.
So you break the big pile of data down into smaller, meaningful piles. Why?
Because sometimes when you analyze the total data set all lumped together, the overall picture might look okay or maybe just show random variation. But when you stratify it, hidden patterns emerge.
Ah,
For example, the overall defect rate for a software release might seem acceptable, but when you stratify the defect data by development team, you might suddenly discover that Team A has a significantly higher defect rate than Team B or Team C.
so stratification pinpoints where the problem actually lies.
Exactly. It helps you isolate the source of variation or the specific area that requires focused improvement, revealing insights that were obscured when the data was analyzed as a whole.
Okay, makes sense. But how do flowcharts fit in? They seem like process diagrams.
Flowcharts, or process maps, are considered a key tool used within stratification or closely related to it. A flowchart visually displays the sequence of steps, decision points, parallel paths, and branching logic within a process.
Right, mapping out the workflow.
Yes. And this is incredibly valuable in IT quality management. By mapping the workflow, you can identify potential bottlenecks, redundant steps, overly complex paths, or areas prone to error.
And you mentioned earlier it helps with the cost of quality.
Absolutely. Once you have a clear flowchart of the process, you can start to analyze the costs associated with each step. You can estimate the cost of conformance activities like inspections, reviews, testing steps designed to ensure quality, and crucially, the cost of non-conformance, like rework loops, debugging steps, handling exceptions caused by failures. The flowchart makes those costs visible within the process flow.
Wow. Okay, it really is amazing how these 7 relatively simple tools, some visual, some basic stats, can bring so much clarity and order to something as potentially chaotic as a big IT project.
They really are the foundation. Mastering these tools takes a project manager and, frankly, the whole team away from guessing and intuition
Towards data-driven decisions.
towards data-driven decision-making. And understanding these tools really sets the stage perfectly for looking at the more comprehensive quality methodologies like Six Sigma.
Yeah, that leads us right into a pretty common debate you hear in quality circles, doesn't it? Is Six Sigma just, TQM repackaged with better marketing, or is it something genuinely different, a real evolution?
That's the core argument you see in the literature. And our sources generally lean towards Six Sigma being a significant extension of total quality management, or TQM. But to see why, we need to understand TQM first, its history and philosophy.
Right. What was TQM all about?
TQM emerged as a holistic management philosophy. Its focus was broad. Continuous improvement across the entire organization, aiming for high customer satisfaction, and crucially, involving all employees in the quality effort.
Everyone's responsible for quality.
That was the idea. It heavily promoted concepts like Kaizen, that Japanese principle of continuous small incremental improvements made by everyone every day.
And it used a specific cycle for improvement.
Yes, TQM relied heavily on the PDCA cycle, sometimes called the Deming cycle. Plan, do, check, though sometimes study is used instead of check and act. It's an iterative cycle for identifying problems, implementing solutions, checking if they worked, and then standardizing the improvement or trying again.
Sounds reasonable.
Yeah.
But you mentioned TQM had a bit of a reputation problem, maybe seen as soft.
That was definitely its main historical criticism. TQM, in practice, was often slammed for being a fuzzy concept. Yeah, meaning it felt more like a cultural initiative, maybe a bit vague. It often lacked a really clear, detailed implementation infrastructure or rigorous mandatory metrics compared to what came later.
So good intentions, but maybe not enough structure.
Often, yes. Many companies adopted the TQM philosophy, the posters, the slogans about employee empowerment, but they failed to fully commit to the underlying statistical tools, or they didn't rigorously train people, or, and this is a big one, they failed to explicitly link the quality improvement efforts directly to tangible financial performance.
So the connection to the bottom line was weak.
It was often weak or missing, which made it hard to sustain momentum or prove value to executives when budgets got tight. Many TQM initiatives faded away because they couldn't demonstrate clear ROI.
Okay, so contrast that fuzziness with Six Sigma. Six Sigma sounds incredibly structured, almost intimidatingly statistical.
It was designed, in many ways, specifically to address those perceived weaknesses of TQM. Six Sigma is defined as a comprehensive, flexible system for achieving, sustaining, and maximizing business success.
How? What's its core driver?
It's relentlessly driven by understanding customer needs, using facts and statistical analysis, and paying disciplined attention to managing, improving, and reinventing business processes. But its intense focus is on the reduction of variation in those processes.
Reducing variation. making things more consistent and predictable.
Extremely consistent and predictable. Its ambition is, frankly, revolutionary. It aims for a level of quality that's near perfection, statistically defined as 3.4 defects per million opportunities, or DPMO.
3.4 defects per million. That's incredibly stringent. That numerical target alone feels very different from TPM's general continuous improvement idea.
It is very different. That target provides a clear, measurable, and universally understood goal for all Six Sigma efforts. And achieving that level of precision demands a highly structured, methodical approach to problem solving.
Which brings us to the Six Sigma improvement cycle.
Yeah.
It's not PDCA.
Right. Six Sigma primarily uses the DMAIC cycle for improving existing processes that are falling below specification or not meeting customer needs.
DMAIC. Define, measure.
Define, measure, analyze, improve, and control.
DMAIC, okay.
It's a closed-loop scientific method. Define the problem and project goals. Measure the current process performance baseline. Analyze the data to identify root causes of defects or variation. Improve the process by implementing solutions. And control the improved process to ensure the gains are sustained.
Very systematic. What if you're designing something new?
For designing new products or processes, Six Sigma uses a related methodology called DMADV: define, measure, analyze, design, and verify. The goal there is to design quality and predictability from the very beginning.
Okay, so rigorous methodology. But you also mentioned structure. Six Sigma seems to involve specific roles. Belts.
Yes, and this is perhaps the most significant structural difference compared to TQM's everyone's involved approach. Six Sigma implementation relies on a dedicated organizational infrastructure, often called the belt system.
Like martial arts belts.
Exactly like that. You have champions, who are typically senior managers responsible for identifying projects and removing organizational barriers. You have master black belts, who are highly experienced experts, trainers, and mentors.
Okay.
Then the workhorses, black belts. These are individuals trained extensively in the Six Sigma methodology and statistical tools, often leading complex improvement projects full-time.
Full-time quality experts.
Often, yes. And supporting them, you have green belts who lead smaller scope projects within their functional areas, applying the tools while still doing their regular jobs. Sometimes you even hear about yellow belts with basic awareness.
That sounds much more formalized than TQM's approach.
It is. This dedicated structure ensures that there's deep expertise available, that projects are managed with rigor, and that the methodology is applied consistently. It provides the leadership and technical horsepower that TQM initiatives sometimes lacked. It treats quality improvement as a serious, strategic business initiative, not just a side activity.
Okay, so we put them side by side, TQM and Six Sigma. They clearly share some core philosophies, right?
Oh, absolutely. Both are fundamentally customer-centric. Both take a process view of work. Both emphasize continuous improvement and the value of making decisions based on data. And both require strong guidance and commitment from top management to succeed. The DNA is similar.
But Six Sigma adds some distinct layers. What would you say is the crucial value add? Where does Six Sigma really go beyond TQM?
I think the key differentiators, the real value add of Six Sigma, lie in a few areas. First, the focus.
How so?
TQM's focus was often broad, maybe on overall customer satisfaction or employee morale. Six Sigma has a laser-sharp focus on reducing process variability. Making the process output incredibly consistent and predictable is paramount.
Less variation means fewer defects, fewer errors.
Exactly. And second, and this is arguably the most critical difference in practice, Six Sigma mandates linking every single improvement project directly to tangible financial results.
Ah, the ROI connection that TQM often missed.
Precisely. When a black belt leads a DMAIC project, the primary success metric isn't just we reduced bugs by 50%, it's we achieved quantifiable cost savings of X dollars by reducing defects, or we increased revenue by Y dollars by improving process throughput.
So it speaks the language of business.
It absolutely speaks the language of the CFO. This financial accountability, this explicit link to the bottom line, is something TQM often struggle to institutionalize. It's what gives Six Sigma staying power in many organizations.
So it's the combination of that intense focus on variation, the advanced statistical toolkit, the rigorous DMAIC-DMAB methodology, the dedicated belt structure, and that non-negotiable link to financial results.
That whole package, yes, that's what takes the foundational philosophy of TQM and turns it into the highly disciplined, data-driven, and bottom-line focused extension that is Six Sigma. It added the teeth, perhaps.
Okay, that comparison is really clear. But whether we're talking TQM, Six Sigma, or just basic PQM principles, none of it works in a vacuum, right? It has to be part of a bigger organizational strategy.
Absolutely. You can't just bolt on a quality program. To truly succeed, PQM needs strategic alignment. And we should acknowledge, that everything we're talking about today stands on the shoulders of giants.
The quality gurus.
The quality gurus, exactly. People like W. Edwards Deming, Joseph Duran, Philip Crosby, Ishikawa himself, Taguchi, Feigenbaum. Their collective work laid the foundation. Deming's emphasis on profound process knowledge, understanding variation, his 14 points, the PDCA cycle he championed. These ideas form the ethical and methodological bedrock of modern quality management.
And their collective wisdom seems to point towards one factor being absolutely critical for success.
Leadership, unquestionably. Time and again, studies and experience show that the primary factor impacting IT project quality and organizational quality overall is the commitment and active involvement of top management.
It's not just delegating it to a quality department.
Not at all. This isn't optional anymore. It's a strategic mandate. And it's formalized in global standards like ISO 9001.
Right, ISO 9001, the big international standard for quality management systems, QMS. What does the latest version, ISO 9001.2015, say about leadership's role?
It's very explicit. ISO 9001.2015 places direct accountability for the effectiveness of the entire QMS squarely on top management. Their role isn't just symbolic, signing off on a policy, it's deeply operational.
What are their specific responsibilities then?
Leaders must establish a clear, relevant quality policy and measurable quality objectives that align with the organization's strategic direction. Crucially, they must ensure that the QMS requirements are integrated into the organization's core business processes.
The quality isn't separate, it's part of how business is done.
Exactly. It shouldn't be seen as a parallel track or a bureaucratic layer on top. It needs to be embedded in the way work actually happens.
And you mentioned risk earlier.
Yeah.
How does leadership tie into that?
That's another major emphasis in the 2015 version. Leadership must actively promote the adoption of a process approach and, importantly, risk-based thinking throughout the organization.
Risk-based thinking, meaning what exactly?
It means shifting from just reacting to problems after they occur to proactively identifying potential risks and opportunities that could affect the conformity of products and services or impact customer satisfaction. Leaders need to ensure this thinking permeates the culture.
So it's about foresight.
It's about foresight, prevention, and also seizing opportunities for improvement. Leaders are also responsible for ensuring the necessary resources, people, tools, infrastructure, budget are available for the QMS to function effectively.
And supporting their people.
Critically, they need to provide support, coaching, and continuous learning opportunities. They need to foster open communication so that every employee understands the quality policy, understands their own objectives, and sees clearly how their individual work contributes to the organization's overall quality goals and customer satisfaction. Without that visible, consistent, supportive leadership from the top, quality initiatives inevitably stall or fail.
That strategic view naturally leads to thinking about cost. Quality efforts aren't free. How should organizations think about the investment?
That's where the concept of the cost of quality, COQ, comes in. It's a framework that helps organizations understand that quality spending isn't just an expense line item, it's a balance. It forces you to look at the total cost.
Total cost meaning?
The cost of quality is generally broken down into two main categories, the cost of conformance and the cost of nonconformance. The total COQ is the sum of those two.
Okay, let's break those down. Cost of conformance, that sounds like the good costs.
Generally, yes. The cost of conformance represents the money you invest proactively to ensure requirements are met and defects are prevented in the first place. It has two subcategories.
Which are?
First is prevention cost. This is money spent up front to prevent errors from happening. Things like quality planning activities, developing robust processes, technical training for staff, conducting design reviews, building automated testing scripts. Investing here avoids problems downstream.
Makes sense. What's the other part of conformance cost?
Appraisal cost. This is the cost associated with evaluating processes and outputs to ensure they meet the standards. Think inspection activities, conducting tests, quality audits, calibration and maintenance of measurement and test equipment. You're spending money to check things along the way.
Okay, so conformance, prevention plus appraisal. That's the proactive investment side. What about the other side? The cost of nonconformance.
This is where it gets painful. The cost of nonconformance is the cost incurred because failures occurred. It's the price of poor quality. And it's also split into two types.
Internal and external.
Exactly. Internal failure cost is the cost of correcting defects or errors that are caught before the product or service is delivered to the external customer.
Like finding bugs during testing.
Precisely. The primary component here is rework fixing the bugs, debugging code, rerunning failed tests, scrapping defective materials, downtime caused by internal failures. It's costly, but at least the customer didn't see the failure yet.
Which implies external failure cost is when the customer does see it.
Yes, and this is often the most damaging and potentially catastrophic category, especially in IT and related fields. External failure cost represents the costs incurred because errors or defects were not detected until after the product or service reached the customer.
Give us some examples here. This sounds bad.
It can be devastating. Think about a major software bug in a financial trading system causing incorrect trades, or a security vulnerability in a healthcare application leading to a massive data breach.
Right. The consequences are huge.
The costs just explode. External failure costs include things like warranty claims, handling customer complaints and returns, product recalls, liability lawsuits, regulatory fines, think GDPR, IPA violations, damage control and public relations efforts, lost customer goodwill, and future business.
And dealing with compromised customer data.
Absolutely. Especially critical in IT. That can include costs for credit monitoring for affected users, legal settlements, and remediation of damage to customer property, which significantly can include their personal data. The failure to invest adequately in prevention and appraisal.
The cost of conformance.
Right. Failing to spend enough there often leads directly to exponentially higher internal and especially external failure costs down the line. Strategic quality management is largely about optimizing this balance, investing smartly in conformance to minimize the total cost by drastically reducing non-conformance costs.
That framework really highlights the business case for quality.
Okay, circling back to strategic alignment, we mentioned ISO 9001.2015 as the global standard. How does it specifically ensure quality gets embedded into the business beyond just leadership?
Well, beyond the strong emphasis on leadership and risk-based thinking, the 2015 version really pushes organizations to understand their unique context of the organization.
Context.
Yeah, it requires the organization to determine the external and internal issues that are relevant to its purpose and strategic direction, and that affect its ability to achieve the intended results of its QMS. Think market pressures, technological changes, regulatory landscape, internal culture, resource constraints.
You can't just copy-paste a generic QMS. Exactly. It has to be tailored. And closely related to that, ISO 9001 requires identifying all relevant interested party stakeholders and understanding their needs and expectations.
Who are interested parties?
It's broad, obviously customers, but also suppliers, owners, employees, regulators, even the community. By understanding the context and the needs of all these parties, the QMS becomes much more relevant, effective, and truly integrated with the organization's overall strategy and success factors. It ensures the QMS isn't just an isolated bureaucratic system.
And these big standards often work alongside other strategic tools, right, like maturity models.
Very often, yes. Frameworks like CMMI, the Capability Maturity Model Integration, are really important strategic tools, especially in software and systems engineering.
How do they help with quality?
CMMI provides a structured way for organizations to assess the maturity level of their processes, typically on a scale from level 1, initial, meaning chaotic and ad hoc, up to level 5. Optimizing, meaning focused on continuous quantitative improvement. It's a roadmap for getting better. It's a roadmap for process improvement. By understanding their current maturity level, organizations can identify weaknesses and implement specific practices to reach higher levels. Higher maturity levels generally correlate strongly with better predictability, lower defects, improved efficiency, and ultimately higher quality outcomes across their entire IT project portfolio. It helps institutionalize quality practices.
Makes sense. One last area here. We've talked a lot about planning, structure, standards, often associated with more traditional waterfall-style projects. How does all this PQM thinking apply in today's world of agile and adaptive environments? Does it still fit?
It absolutely still fits, maybe even more importantly. Quality remains one of the 10 core project management knowledge areas identified by PMI, regardless of the development methodology you're using, waterfall, agile, hybrid, whatever.
But Agile is all about flexibility and responding to change.
It is. But the fundamental goal of PQM doesn't change: ensuring the project satisfies the needs for which it was undertaken. In Agile, the way you achieve this is different. The PQM processes planning, assurance, managing, control are still there, but they're cycled through much more rapidly and iteratively, often within each sprint or iteration.
So quality isn't just a phase at the end.
Definitely not. In Agile, quality is built in continuously. Requirements might emerge and evolve, but the team constantly works to ensure the deliverable meets the current understanding of those needs and is fit for use now.
How is that achieved practically in Agile?
Through practices like continuous integration, CI, automated testing embedded in the development pipeline, frequent demonstrations of working software to stakeholders, collecting rapid feedback, and techniques like test-driven development, TDD, or behavior-driven development, BDD. Quality isn't a separate gate. It's an integral part of the definition of done for every user story, every sprint. The focus is on preventing defects through collaboration and automation rather than just finding them later. Hashtag outrag outro.
Okay, wow. That was a really comprehensive deep dive. Let's try and synthesize this a bit. We started by really nailing down the structure of project quality management.
Emphasizing that crucial difference between just conforming to some spec versus achieving true fitness for use. Does it actually work for the user?
Right. Then we got tactical. We walked through those 7 basic tools of quality, the practical toolkit you need for process control.
Yeah, everything from tracing root causes with the fishbone and the 5 whys, right through to using the Pareto chart to focus your precious resources where they'll have the most impact.
And we definitely didn't stop at the basics. We really dug into that comparison between TQM and Six Sigma.
Identifying Six Sigma's disciplined, statistical power, that rigorous DMAIC cycle, the belt system providing expertise, and that absolutely critical link to financial results.
As the necessary evolution, the extension, that addressed some of the organizational weaknesses people sometimes saw in TQM. And then finally, we tied it all together by grounding everything in the bigger strategic picture. The absolute necessity of strong, committed leadership.
Understanding the cost of quality not just as an expense, but as a strategic investment balance.
And aligning with global standards like ISO 9001.2019 with its focus on risk-based thinking and organizational context.
And hopefully this whole discussion moves you, the listener, beyond just knowing the definitions. It gives you the framework, the skills to evaluate complex quality situations you'll face.
And apply these concepts and techniques directly, especially thinking about that practical group project you're working on. This gives you the tools for the quality phase.
Absolutely. You should feel much better equipped now.
Okay, so before we wrap up, here's that provocative thought to leave you with. Something connecting all this quality rigor back to real-world IT accountability.
We've established that modern standards like ISO 901 explicitly put the responsibility for quality, for risk-based thinking, on top management. So consider this. If a massive catastrophic system failure occurs, think a huge data breach, a critical infrastructure collapse. Is the ultimate root cause just some technical bug buried deep in the code? Or is the deeper root cause actually a failure of the management process? A failure to implement the necessary quality controls, the statistical reviews, the prevention investments we've been talking about. A failure to foster a quality culture.
And if it is a management process failure, who ultimately is held financially and strategically responsible for that failure of quality management?
It's a heavy question, but the answer really determines not just the fate of that one project, but potentially the reputation and viability of the entire organization.
It really underscores the strategic importance of everything we discussed. Behind every successful app launch, every seamless online order, every tech innovation you rely on,
there's IT project management making it possible. And a huge part of that is the rigor and discipline of quality management.
Couldn't have said it better.
Until next time, keep exploring this fascinating world where ideas become projects, and those projects genuinely shape our future.